Alright kiddies, welcome to video 9.4. Our learning objectives for this particular lesson are neutralization reactions, calculating the pH of strong acids and strong bases in reaction, and understanding something about the pH curve. So let's get started. Okay, so we have talked about this before, that when I take an acid and I react it with a base, the hydrogens are going to react with the hydroxide ions to form water. So we have hydrogen ions reacting with hydroxides to form water. So what happens if I add a strong acid and a strong base? It is what is called a neutralization reaction. So that is the net ionic for any strong acid or strong base reaction. Suppose that I have 210 milliliters of a 0.30 molar hydrochloric acid solution, and to that I add 150 milliliters of a 0.4 molar sodium hydroxide solution. What would be the pH of this resulting solution? So this goes back a little bit to our discussion on solutions. We want to know what the pH is, so we need to know what concentrations are. To know concentrations, we need to know moles per liter. So if I go back to our HCl solution, I know that I have 0.210 liters, and the concentration is 0.30 moles of HCl per every 1 liter. And I'm going to add one more conversion factor on here that's going to say every 1 HCl contributes 1 hydrogen ion. That's 1 H plus there. There we go. So the answer to this question, there are 0.063 moles of hydrogen present. I'm going to do the same thing with this hydroxide ion solution. So I'm going to go back and say, okay, my volume times concentration. I have 0.150 liters of sodium hydroxide. There are 0.40 moles per liter NaOH. I'm going to add that other conversion factor on where I'm saying for every 1 NaOH, there is 1 hydroxide ion. And that might be different because I might be dealing with like calcium hydroxide, which is CaOH2, which means there's 2 hydroxides for every calcium hydroxide. The answer here is 0.060 moles of hydroxide. So we're just going volume times concentration to get moles of hydrogen, volume times concentration to get moles of the hydroxide, and we're also adding that other conversion factor in where we're looking at how many hydroxides or hydrogens can it donate. So one of the important things when we look at this reaction, if I've got hydrogens and I've got hydroxides, and they're reacting together to form waters, this is a limiting reactant problem, a Lockery-Berger problem, in a sense. So let's think about this for a second. If I start a reaction with 90 hydrogen ions, and I react that with 100 hydroxides, what would form? Well, we'd end up with 90 waters, and we'd have 10 hydroxides remaining. Suppose I start with 160 hydrogens, and I only have, 50 hydroxides. Well, that would mean I can only form 50 waters, but that would leave 110 hydrogen ions remaining. So we're going to kind of look at the math that way. Oh, there we go, 110. If then I were to react 0.063 moles of hydrogen with 0.060 moles of hydroxide, what would be left over? Well, in a sense, I'm not really going to add those guys, am I? What I need to do is subtract one from the other to figure out what's left over. So if I subtract the moles of hydrogen, the moles of hydroxide from the moles of hydrogen, I will have what remains in the solution. So this is going to become a subtraction problem. So obviously I end up with 0.003 moles of hydrogen remaining. So we subtract the smaller from the larger to determine what's remaining. Now this is moles. We want concentration. So I'm going to take moles and divide by total liters. What did I have? I had 210 milliliters here, and I added 150 milliliters here, so I end up with a total of 360 milliliters, which is 0.360 liters. So now dividing my moles by my liters, I get a 0.0083 molar hydrogen ion concentration. Now obviously we're looking for the pH, so I'm going to take the negative log of this guy to get pH equals pH, and that guy is 2.08. So it's still acidic at that place. Obviously, because I had more hydrogens than hydroxides when I put them together, it ends up being acidic. So volume times concentration, that gives me moles. Figure out how many hydrogens it can donate per each unit. That gives me moles of hydrogen. Volume times concentration here, that's going to give me moles of NaOH. Multiply by the number of OHs in that particular compound to get moles of OH. Subtract the larger from the smaller. Divide the remaining moles by the total volume. Then the negative log of that gives me the pH if I had excess hydrogen. It gives me pOH if I had excess hydroxide. So what we're going to do now is take a look at how the pH changes during a titration. So we're going to look at a pH of an acid-base titration curve by adding a volume of base to an acid. You'll notice my pH scale going from 0 to 7. 7 is when I have equal moles of acid and base. So we're talking about a strong acid and base here. If I start with pure acid, its pH is going to be very low. But as I move through the titration, adding more and more base, you'd probably expect the pH to increase, hitting 7 at the point where I have equal moles of both. Then anything that I have in excess to that acid, any more base that I add, will make it more and more basic. So we're going to take a look at that for a second. So what I've done here is I've made a PowerPoint to calculate the pH at various points through the titration. So the data that I've plotted here is the volume of the acid that we start with. You'll notice that it's 0.025 liters. So I'm starting with a fixed amount of acid. Then we have the volume of base in liters here. So I slowly am increasing the amount of base to see that rise. We're going to use a 0.1 molar acid and a 0.1 molar base. Now here's the interesting thing. I can calculate the hydrogen ion concentration through here very easily. So I want you to look at this calculation in this little box at the very top. If you can see where my mouse is wiggling. I have A2 times C2 is my first calculation. That means I'm taking this number in cell A2 and multiplying it by C2. Why would I do that? Volume of acid times molarity of acid. So that's essentially just finding moles of acid. The second thing is I'm subtracting B2 times D2. B2 is the volume of the base, D2 is the molarity of the base. So essentially this first part of the calculation right here is just saying moles of acid minus moles of base, but more specifically the hydrogens and hydroxide ions. Then I'm taking moles and I'm dividing by A2 times B2. What is A2 times B2? That is the sum of the two volumes. Why? Because I'm adding the acid to the base, so the molarity is going to be the moles divided by the total volume. So this gives me a look at the last cell over here is just the negative log of whatever is here. So this is my pH column. So this is a handy way to do things if you've ever used Excel. If we were in class, we'd be doing that right now. So when I start, I don't have any base. My pH is starting at 1. And as I add more and more base, the pH, as we expected, is slowly starting to go up. But there's some surprises here. For example, if I look down here, there's 25 milliliters of acid, 23 milliliters of base. Only 2 milliliters difference. You'll notice that the pH is only 2.38. Wouldn't we expect that to be a little closer to 7? Let's go a little closer. Here's my 25 milliliters of acid. I've added 24.4 milliliters of the base. My pH at that point is only 2.916. Well, aren't they supposed to reach 7? We're really close to that equivalence point, but our pH is still really low. That's just crazy. So we go way up here. Here's 25 milliliters. I'll even go one further. 25 milliliters of the acid, 24.94 milliliters of the base. We're almost at the equivalence point. 0.06 of a milliliter, and the pH is only 3.92. And as I get closer and closer, hey, look what happens. 0.02 of a milliliter, it's only, or 200 of a milliliter difference. The pH is only at 4.3. Right when they get equal, 25 milliliters of each, because their concentrations are equal, we end up with a pH of 7. So this is a little funky. I want to take a look at this as a graph for a second. So when I actually graph this pH, so my pH is over here, as my ooh, that's weird, pH. It's kind of cool though. As the increasing volume of base across the bottom, you'll notice that the curve is not linear at all. It looked nothing like what we said it was going to look like. What kind of curve looks like this instead? What kind of curves do we call those? It's a logarithmic curve, an exponential curve. And what about going in this direction? That's also a logarithmic curve. Why would these be logarithmic curves instead of linear relationships? Because what are we doing? We're doing the negative log. We're doing the pH. This is a logarithmic function. So what's cool about this is when we're doing acid-base titrations, there's a very slow increase in the pH until we get near that equivalence point, and then a huge rapid change in the pH with only a couple milliliters of change. I mean, not even a couple milliliters, as you saw. A couple hundredths of a milliliter caused a huge change. So we see very dramatic changes in pH as we move through that equivalence point. That's just so exciting, isn't it?